So in this video, we're going to talk about how do we draw Lewis structures for organic formulas, right? So let's say that you're given N2H4 on an exam. How would you draw the Lewis structure for N2H4? Well, the fact that for this, how would you tackle it? The fact that you know that hydrogen can only form one bond, it would be plausible to not place hydrogen in the middle of the structure. So in fact, intuitive would say that, okay, well, I'm going to put a nitrogen and I'm also going to put a nitrogen beside each other, right? Now, from here, I could actually form my hydrogens, right? And at this point, we should be comfortable with actually forming, knowing that hydrogen can only form single bonds, right? Because it only has one valence electron. Now, remember, we still have to satisfy our octet rule, right? So the first thing I'm always going to do, and in fact, I didn't obey the rule this time, but usually what you want to do is you want to be able to count the number of total valence electrons that you have to place in the molecular formula. So in this case, I know that I'm going to do 2 times 5, right? Because nitrogen has 5 valence electrons, and we know this comes from general chemistry. So 2 times 5, I have 2 nitrogens, so that would be 2 times 5, plus 4 times 1 valence electron that hydrogen has. We have 4. Hydrogen each gives you 1 valence electrons per piece, but we have 4, so we have to multiply. So this becomes 2 times 5, which is 10, plus 4, so that'd be 14 electrons total that we have to place. So let's see how much have we placed thus far. We've placed 2, 4, 6, 8. Right? So we still need about 6 more to get to our target. So in this case, I'm going to start and form a single bond between my 2 nitrogens. Right? In this case, now I have 2, 4, 6, 8, 10. Now, I'm missing 4 electrons, and my nitrogens are not satisfying the octet rule. We know that our hydrogens are good at this point, right? So what I'm going to do is I'm actually going to put a pair of lone pairs on each nitrogen. And let's see if we have 14 electrons. Let's see if our octet rule is satisfied. So in this case, I have 2, 4, 6, 8. 10, 12, 14. So this would be a plausible Lewis structure for N2H4. Now, if you wanted to put a double bond between the 2 nitrogens, you would have seen that it probably wouldn't have worked. Even though the nitrogens most likely octet would be satisfied, you'd be missing two more electrons. So there's no way you could actually put a double bond in between. Let's do another one. So let's say you're given CH3 in parentheses NH2Cl. How do we tackle this on an exam? How do we actually draw it? Well, the way I read this is that usually when your method groups or whatever group is placed in parentheses, that usually means they come together as one. So that means that they're bonded to something. Now we could imagine we probably most likely have 2 methyl groups being bonded to our nitrogen. Again, we know that hydrogen can't be in the middle, right? Because it only forms 1 valence electron. And so I want you to think about organic chemistry in that fashion. And then we have chlorine out here that honestly could be placed anywhere, right? So I'm going to choose nitrogen in this case as my central atom. And like we said before, we have 2 CH3 being bonded to our nitrogen atom, right? Again, usually like we said before, if we have anything that's in parentheses together and the subscript means that we have two in this case, they're usually bonded to a single atom. Now I've placed my CH3, I've placed both my CH3s, I've also placed my nitrogen. Now I need to place 2 hydrogens, right? And so in this case, hydrogen can only form 1 bond. So here is my hydrogen. Now, if we look at this without even calculating our valence electrons, right, because that would be a lot, but looking at this, this would be 2, 4, 6, 8. electrons. And so you would say that the nitrogen is actually full. And so in fact, we cannot actually even put any more electrons bonded to our nitrogen. So this one is a tough one. So nitrogen valence is full, so we can't put any more electrons to bond to the nitrogen. So where does the chlorine go? This one is a tough one. The only other place we could put the chlorine is actually to put it as a negative charge, and we have the nitrogen being balancing out the chlorine as a positive charge. And in fact, this should make sense because again, our total molecular formula is actually neutral. There are no charges, right? So a positive plus a negative is equal to that is neutral. So this one was a tough one. How do we tackle this one? CH3 and CO. Well, I'm always going to look at a CH3 as just being one unit. And in fact, you could actually look at it as a CH3 maybe being bonded to the nitrogen, and the nitrogen be bonded to some sort of CO. Right? So if I place the nitrogen in the middle, then I could see that CH3 in this case forms a single bond. I'm going to try to satisfy the nitrogen octet rule, so maybe my nitrogen is bonded to carbon. Now again, I want you to get comfortable with a lot of times Lewis structures are kind of trial and failure. Right? So there's no single way of going about it. But again, I've given you some sort of clues as to how you would actually tackle these sorts of problems. Now, because I need nitrogen octet to full, and you can see that I'm probably going to put a oxygen here. Because I need nitrogen octet to full, I'm probably going to form a double bond between the nitrogen and the carbon. Now that gives me 2, 4, 6 electrons around my nitrogen. Right? Now I could place a lone pair around the nitrogen, and this would give me 2, 4, 6, 8. So I know that at this point my nitrogen is satisfied. What about my carbon? It only has 6 valence electrons around it. My oxygen only has 2 valence electrons around it, so that's not satisfied. So if I form a double bond between the carbon and the oxygen, now my carbon is satisfied. I have 2, 4, 6, 8 electrons, and I could put 2 more lone pairs in the form on the oxygen, and that would give me the molecular formula that we're looking for. Again, at this point, if you want to make sure, you could actually add up your total number of electrons that should be there in the molecular formula. So if you want to be technical, we know that carbon gives us 4 valence electrons. We have hydrogen that gives us, well, in this case, 3 times 1, right? Because we have 3 hydrogens. Nitrogen gives us 5 valence electrons, so we only have 1 nitrogen. Again, carbon actually gives us, we actually have 2 carbons, so it could actually just multiply this by 2. And then we have an oxygen that gives us 6 valence electrons. So if you're not comfortable getting the atomic or the Lewis structure by not calculating, you could just try to make sure that you're actually right. And so these numbers that we calculate should equal to the total number of electrons we've placed in our formula. So 2 times 4 would become 8 electrons for carbon plus 3 electrons. 3 times 1 is 3. For nitrogen, for hydrogen, plus we have 5 electrons for nitrogen plus 6 electrons for oxygen. So this is equal to, okay, 16. We have 16. So this would be about 22 electrons, right? 8 plus 5, that's 13. Plus 3, that's 16. Plus 6, that should be about 22 electrons. Let's see if we have 22 electrons, right? We have 2, 4, right? We have 2 right here from the oxygen. So we have 2, 4, 6, 8, 10, 12, 14, 16. Now remember, the carbon, we didn't write out the electron, the bonds explicitly. But if we want to write out the bonds explicitly, we have a CH3 bonded to nitrogen, that's double bonded to a carbon, that's double bonded to an oxygen. All right, and so if we count the formula, if we count the bond in here, this becomes 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. And so this would be a plausible Lewis structure for the CH3 NCO molecule. Right? So again, our calculation here is just something that if you're not comfortable, you've gotten the formula right, you could go and calculate. And remember, this must match, right? So if I count 22 electrons, but only 21 is supposed to be there, or vice versa, then it's wrong. How would we try this from the line angle formula? So CH3OSO2 OCH3. How would we come up with the Lewis structure for this? Again, I usually read these from left to right. So I see a CH3, I'm going to group it together. I see a CH3 on the other hand, I'm going to group it together. Now, you got to be able to visualize. I see that oxygen is most likely bonded to a sulfur atom that has 2 oxygen on it. And then this oxygen is bonded to another CH3. All right. So I'm going to start out at the end. Right. So I have a CH3 that's most likely bonded to an oxygen. So I'm going to form a double bond. I'm not going to form any double. I'm not going to. I'm sorry. I'm going to form a single bond. Not going to form any double bonds at this point. I just want to start from the lowest number of electrons and then move up. Now this oxygen, in all likelihood, is most likely going to be bonded to a sulfur. Now what the formula is telling you is that this sulfur contains 2 extra oxygen on it, right? So I could form a single bond to each oxygen, and there goes my SO2. Now I could also see that sulfur is bonded to another oxygen, and I could see that this oxygen right here is bonded to a CH3. Now, if you want to make sure you get this right, you do the calculations like we said before. But I can see that in this formula, there are several things that are missing the octet rule. And so if I look at this oxygen right here, I see that it only has 2 4 electrons around it, right? So I could put 2 pairs of lone pairs around this oxygen, and this would make this oxygen 8 electrons. So we know we're good in this aspect. I could also do the same thing for the other oxygen. So this would be 2 4, right? And so this becomes 2 4 6 8. So this oxygen is satisfied as well. How about the oxygen on the sulfur atoms themselves, the 2 oxygens? Now remember, from general chemistry, we learned that sulfur is one of those groups that can potentially have an expanded octet. So we shouldn't be surprised if our sulfur actually has more than 8 valence electrons. At this point, we're looking at it, it has 8 valence electrons. Now I can actually form a double bond between the sulfur atom and the oxygens. And now my oxygen has 4 valence electrons around them each. So now I can actually put 2 pairs of lone pairs on each oxygen, and that will give me a total of 8 valence electrons around the oxygen. And so this would be a plausible Lewis structure for or line for or a bond angle formula or written formula. Right? Again, to make sure you're right, if you're not comfortable, again, you could do the calculations with respect to the number of valence electrons, and that will confirm that you are correct.